Hello, and welcome back to the Empowerment Project. This session is going to be about a process called polynomial regression. This is a process that many people would need to use for biological data analysis because biological data don't always respond in a linear fashion. Sometimes they have a more complex response. And this is just going to be an introduction to this concept and showing you a little bit about how to go about this type of analysis. First, you'll want to turn on your libraries. We're going to use GGplot and Grid Extra. Obviously, if you don't have those, you'll have to install those first. Okay, I'm going to provide you with a CSV that's some plant diversity data. So you can bring in those data however you like. You can bring them in using the import data function or whatever way you want to do that. And then I always take a look at the data whenever I bring data in like this. And so in this case, we've got a 3 columns plot. This is where measurements were taken, and we have two variables, cover and diversity. Cover is a measure of how much space is being taken up by plants on that plot, and diversity is the botanical diversity of the plot. Okay, this is what the data set looks like, and the first thing you might like to do in such a situation would be create a scatter diagram of the data like this. So I'll let you take a second and create this scatter diagram. So pause the video, type the code. Okay, got it. So as always, when you look at, well, first of all, the code is simply div is the data set, and then x is cover, y is diversity. Over here you can see my cursor, diversity and cover. As the cover increases, diversity increases at the start, and then is leveling off here. So just like a quick analysis of it or a visual inspection of the data set, thinking about effects, distribution, outliers, variance, effects, sample size. The quick thing to say here is that it looks like you've got a linear response at the start, and then it's leveling off as we increase the cover. Now, the first thing you would do in an analysis like this, with a scatter diagram like this, and there are biological reasons to expect that this would be what happens, that you would have a relationship like this, a linear relationship at least at first. One thing you would want to do is draw a line through that, and you could do it like this. So this is a straight line fit. So play a little coding music while you work on that. Okay, got it? Not sure if you could hear that or not. That was some music to help you code. Now, what you have here now is a linear regression through this cloud of points. See my cursor? And here's some specifics. I'm using method equals LM, color equals red. So this is just drawing a red line through the points. The gray is the 95% confidence interval. So now, one thing you would do for a linear regression, there's different ways of going about this. There's many different ways, as there are with everything we do in this package. There's many different ways to do this. This is one way to do it, which is just to define this straight line fit. So this is basically creating the mathematical line, this fit. So we'll do it like this. Linear fit equals LM. This is linear model, diversity, cover. And the data is, and there's a little tilde here, diversity by cover. And then data equals div. So you're pointing, this is just pointing to the data set. So you'll type up this code And you're defining this linear fit as this relationship, which is a linear, this as a linear model. It's using this data set div, which is the data set you just brought in. And then you can test this regression, just asking for a summary of this. And then you will get this. Here's the call, and then here's all the statistics. And here we have a statistically significant linear relationship. The p is P0002. And then we can look at the r squared being 0.16. So you go, okay, this is a statistically significant straight line fit. So pause the video and run this code. Okay, got it? So in a lot of biology, this would be this is quite normal. Okay, we've got biological data analysis. You go, oh, okay, we've got one variable and another variable. There looks to be a positive relationship. It's not a flat line. There's increasing. See my cursor here. You're increasing as a cover increases, diversity increases. So we've got a linear fit through this. However, just looking at the data, again, visual inspection, you go, well, this looks good, but this relationship seems to bend here. There seems to be some shape to this curve. It's not just a straight line fit. And so what we have here, and we've done the test, we have a significant straight line fit. However, the data seem to have a curved shape. So we can explore the relationship and test the possibility of a curved relationship using what's called polynomial regression. We can do this actually quite simply, so just by adding this formula. So now let's code up. I'm going to sweep this plot. Let's code up a curved fit this time. So in this case, we're going to go. This is all just GGplot, aesthetic element, x and y, g on point. Then in the stat smooth call, we're saying linear model, but the formula now is a polynomial fit, and we're putting this here, so we're saying there's a squared element to it. X is squared. And then color of the line is red, and now this curve or this line has a curve to it. It's shaped like this. That seems to be a better fit for the data. So let me play a little music while you code that up. Hopefully that didn't fry the speakers. And instead made it so much nicer to make this code. So once you've got that, oh yeah, we can keep or remove the 95% confidence band. So this is a different kind of fit. This is a polynomial regression. So now we come to the question of which fit is better. And there's a lot of ways to go about this. I'm just going to talk about it in a general sense. Using the phrase that I was taught a long time ago, which is regression diagnostics. And this brings us to the concept of Occam's razor. Hold a second. I happen to have Occam's razor here. This is what it looks like. Occam's razor is used to cut away complexity. The basic idea is the simplest solution is the best solution. And when you add a polynomial line rather than a straight line, you're making a more complex solution. So you need good justification for doing this. You can't just do it without considering that you're making the model more complex. Okay, so how do we do that? How do we justify a curved fit versus a linear fit? And so their basic ideas are this. Number one, we can run the fit, this a curved fit, and check it out. And it should be a statistically significant model. And the second thing is we can look at the r squared. And what we're going to try to accomplish is to increase the r squared significantly. Now, to my knowledge, or at least I don't know of an r squared increase cutoff. Okay, so this is going to boil down to some investigator decision making and applying Occam's razor, but also trying to make the strongest fit possible, and also just being transparent in the approach. And again, you may find some other way of doing this where there's more of a regimented rubric or something. But for the purposes of what we're doing here, I'm just going to just kind of talk you through this and see where it ends up. Okay, so we already defined the linear fit this way. We did this earlier. And we tested that linear fit using this summary linear fit like this. So I already showed you this before. This is the code from above, which is just like, okay, here's the call, here's a statistically significant model, and this is the r squared 0.16. So let's now see what the line in the fit looks like if we look at the curve, which is a quadratic line. And so we're going to call this quadratic fit. So this is the code. I'm just calling it quadratic fit equals LM, which is linear model, diversity, cover. Now I'm adding another element to the equation. I'm saying cover squared. And data, again, equals div. So we can define this quadratic fit this way. And it'll just pop up in your console saying, okay, yeah, I know what that, I understand. And then we can ask for a summary of it this way. So type the code and run the code. Okay, pause the video, run the code, got it. Okay, now let's take a look at the result of this summary. So this is like, give me the statistics of this quadratic fit, and we can look at it right here. So now it shows you the call. So we've got this extra element, which is cover squared, and then it shows you down here in this sort of table of coefficients that this is a highly significant model. So it's negative 0.5, so it's 0, 0, 0, 0, a lot of zeros before the 4. Also note that our multiple r squared here has increased, it's doubled. So we went from 0.16 and now we're looking at this as 0.32. So we've doubled the r squared. This is a strong increase. It means your line is a much better fit for this cloud of points. In this case, you could use that to justify the curved fit, the polynomial regression. Okay. So let's now compare these two lines on the same graph. So now, and you can just copy and paste from up above. You can just go grab the equations for stat smooth or the code for stat smooth LM and stat smooth with a polyfit like this. And I made the line type here dashed and the color blue for the linear fit, and then left this red for the curved fit that looks like this. So now you can see them both on the same graph. I think this is nice to compare. So you can go ahead and code that up. That make the coding better? Okay. I'm not, and I use this SE false to take off the 95% confidence interval, just to make it a little bit clearer to see. From this graph, you can see, okay, here's the linear fit, here is the curved fit, and out here, in this range, actually across the range, the red line's better. It's more in the center of the cloud of points. So again, you would have a pretty strong justification for keeping this to be a polynomial model in your final report. Now, we can also add even more complexity to this. I'm going to sweep this now. Even more complexity to this relationship by adding an actual cubic fit. So we have x to the 3 down here, and it's going to look like this. So now we're kind of serpentine snaking through the points. And the way you would do that is, again, using the same code as before, g on point, stat smooth, lm. The formula now is y polyfit. This is a polynomial fit, and we're saying x3. So this is going whoosh, whoosh, whoosh. That's a quadratic. Oh, that's the cubic model, sorry. So go ahead and type this code. Okay, just to assess now, it looks like maybe a little bit better fit, except this dip here is kind of weird. Like you're like not surrounded by the points here anymore. So it's a bit outside the cloud, actually. It would be hard to justify this. One thing to say is that once you add, the more curves you add, the tighter the line will be in some areas, but it might swerve. Like here we're swerving outside in other areas. Let's compare these fits now. Here I've done, again, the top is just the basic g on point. And then I have two functions here. One is the orange. This is color orange. This is polynomial fit. And then I left red for this polynomial fit that's 2 instead of 3. So this is the quadratic, and this is a cubic model. So you can run them both like this and just put a plus between them to connect them, and then you can see them both on the same graph. So type the code, run the code. Got it? What we're doing here is regression diagnostics. Now, when you compare and contrast these two, the red and orange are kind of overlaying here. Maybe the orange is a slightly, even the red looks better. It's like closer to the middle of the points here. And you can see the red line is in the center of the points all the way through this. So it looks like maybe you would slightly increase the r squared, maybe not even, barely, with the orange fit. Generally, when you add another curve to it, it's going to improve the fit. But it doesn't really seem helpful. So we can continue with the statistical diagnostics by doing this. Now we're adding this third layer to our equation. We go cubic fit equals LM diversity tilde cover plus I. This is like one factor is raised to the 2 here. This is the second factor raised to the 3. That puts the cubic fit into it. And then the data again is pointing back to diversity. So we can run this model like this, check it down here. When you see the blue in the console, it means I did that. Say, okay, yeah, I did it. And then we can ask for the summary like this. So now what it adds, it does indicate, this analysis does indicate that this is a statistically significant line. However, our r squared here only increased from what was at 0.32. We can scroll up if we want to look at that again. To 0.37, so it increases almost not at all. It doesn't really change and make the line fit better. And in the meantime, we need to think about Occam's razor. The more complex the line, basically the worse it is, because ultimately when you do regression, you want to be able to make predictions from the regression line, and this curvier it gets, the less able you are to make a prediction based on the equation. So Occam's razor would say slice away the cubic fit and stick with the quadratic fit. And we can, of course, look at these quickly by just hitting summary again, and summary again. And you can kind of scroll up and down and look at the three outputs. And all of this, by the way, so for example, r squared of the cubic fit is 0.37, r squared of the quadratic fit is 0.32, r squared of the linear fit is 0.16. So you go, okay, we doubled by making it curved, increased by a little 0.05, I guess, to make it snake serpentine, doesn't justify basically the model complexity. That's what I would say. And then we can compare all the lines this way. Put them all on the same graph. By the way, this is just something that you might like to do in your life anyway, coding multiple lines on a graph like this. So type the code and run the code. Got it? So you have to use critical thinking and apply Occam's razor. In this case, a quadratic single hump relationship greatly increased the R squared as opposed to the straight line fit. However, there's a little extra power by adding a second curve to a cubic line. The conclusion would be stick with the quadratic fit and then go forth with a line like this. And you can put a line like this in your peer-reviewed journal article and publish those results. I've done this before. Okay, so before we go on, one quick thing I want to say is GGplot does offer you this opportunity for a low S fit, which is super curvy. It's like a local a line that's very respondent to local changes. This would have a very strong R squared because it's infinitely flexible. Basically, it's a flexible spline. However, again, if you try to put this equation and then make a prediction from it, it's going to be too complex. Like this is heading up this way and then suddenly jerks down. So you fall off the line pretty quickly. I just generally would never use a low S with a data set like this. It's nice if you've got a bunch of different, like, oh, I've got 6 panels and I want to generally see where the line's going. It has specialized applications, but I personally, from an Occam's razor perspective, would not want a super convoluted line like that. Okay, now I'm going to ask you to try it on your own. I'm going to give you a productivity data set, pond productivity, from Whitlock and Schluter. This is a textbook, example 17.82. I'll give you the data set, and you can code up your analysis following the same method that I just demonstrated. So hopefully this was helpful, and we'll see you next time.